Thank you for joining us for how to build autocomplete search for e-commerce with Tejaswi Tenneti. Tejaswi is the Director of Machine Learning at Instacart, and he'll be introducing the architecture of e-commerce search and autocomplete systems using Instacart as a case study. If you're interested in more of how to build search engines, you can check out CoreRise's search track starting on February 6th. And with that, Tejaswi, take it away.
Hey everyone, Barbara, thank you for introducing me and having me here. I'm Tejaswi, I'm from Instacart. Today, I'm going to be talking about building autocomplete for e-commerce. A bit about me, I'm currently leading the machine learning team for search and discovery at Instacart. Our team creates machine learning models that power core search functionality, including autocomplete. We apply and invent state-of-art machine learning techniques to exciting problem areas such as user intent understanding, neural text modeling, and multi-objective ranking. Instacart, for those of you not familiar, is the North American leader in online grocery delivery, offering delivery and pickup from your favorite stores in as fast as an hour. Our mission is to create a world where everyone has access to the food they love and more time to enjoy it together. Coming to the topics I'll be talking about today, I'll start with the motivation about what is special about autocomplete for e-commerce. I will cover some of the product surfaces and goals for each of this surface that we usually see autocomplete on. Then I will briefly cover how autocomplete works, especially the architecture and the algorithms. Then I'll cover implementing autocomplete functionality for e-commerce in order to meet any certain desired product goals that the retailer might have. I'll use Instacart as a case study to illustrate my point here, right? So to start off with, what is special about autocomplete for e-commerce? At a very basic level, autocomplete is a feature that assists users with completing their queries faster and saving their time. Generally speaking, web search like Google is optimized to find information on the web, while e-commerce search is optimized for finding products or services on an e-commerce platform. This means we need to go beyond predicting users' queries and guiding the users in their shopping journey. The query suggestions or the autocomplete suggestions need to be personalized to the user's taste. We also need to help users discover new categories of products that they have not shopped before. So in summary, we probably need autocomplete to accomplish both user-specific as well as any platform-specific objectives or the e-commerce retailer-specific objectives as such. For example, we may use it to promote any specific brands and increase ads revenue, or we can also use it to accomplish a core value or any mission of a company. If you take the case of Instacart, it can help customers find like healthy food options, right? To get things started, let us look at like the first product surface that we see for autocomplete surfaces and so on. So this is called like the blank state or the null state, where query suggestions are shown to the user to spark ideas even before the user starts typing in their query. Flavors of the query suggestions that are shown on the surface generally tend to be trending queries or popular queries. They're also usually personalized to the user's taste. We can also use this to achieve any specific product goals, like I described earlier. This is not the focus of today's talk, but however, I would love to call this out as like a very useful surface for e-commerce platforms to achieve both user and platform specific goals, right? Moving on to the next product surface and the main topic for today, autocomplete, also known as type ahead, is extremely useful for an e-commerce platform. Along with helping users save time, this feature is very useful to achieve platform-specific goals like basket building and discovery. Right. So basket building refers to the process of helping the users find the products they want, make smart purchase decisions, and ultimately check out to place an order. Autocomplete helps in this process by deeply understanding where the user is in their current shopping journey. Combine this information with users' historical taste preferences, what kind of dietary preferences they have, what kind of brands do they like, and so on. And start giving suggestions to help them in the basket building process. Now, how does this help the e-commerce platform? Generally making it easier for users to check out tends to drive more revenue and retention. Conversely, autocomplete is also like a great lever to shape the customer shopping behavior itself. For example, it can be used to nudge users towards new categories of products that the user does not usually shop for. Discovering new products and the diversity of the items that are shopped and so on as such generally tends to keep the users engaged, and it drives more retention on the platform. We can also move beyond showing just query suggestions and directly show products or brand images, which can help with merchandising any specific set of products as well, right? Now let us look at how a typical autocomplete looks like from like a systems point of view. There are two important design goals here, right? First is the system should be highly responsive and return query suggestions as fast as possible before the user can manually complete their query, right? This is best achieved by indexing the suggestions in an in-memory storage. Therefore, the system that we design should also be as memory efficient as possible in order for us to scale, because you're holding all of the suggestions in memory, right? So that is the first goal. The second goal would be to provide the suggestions should be like as relevant to the user as possible, which means we need a way to retrieve all possible matches first, and then rank the suggestions, the query suggestions appropriately, right? The simplest method for ranking all of the suggestions, for example, could be to sort the suggestions by popularity. So we need to support a data structure. The database that holds all of these suggestions needs to support a data structure like a sorted map, so that you can sort all of the suggestions in real time in a very low latency setting, right? So the basic functionality really boils down to generating a set of query completions corresponding to a prefix query entered by the user. For this, the first step is to generate a set of query suggestions, a comprehensive data set of query suggestions. Typically, this would be derived from historical search queries, names of brands, product categories sold by the retailer, and so on. The query should then be indexed in a data structure, like I mentioned, that is suitable for achieving our design goals. Most implementations out there use a data structure called weighted finite state transducer for this purpose. We do not have time to dive deep into the details, but I highly recommend looking into an excellent paper on this topic by eBay. This was recently recommended to a colleague by me. It's also linked in the current slide. Sorry, excuse me. So you can create a simple POC for autocomplete using a tool called Elasticsearch. Elasticsearch, for those of you who don't know, is like a very popular platform which provides search engine functionality. It offers autocomplete functionality out of the box, and it's pretty easy to get started with in a few lines of code. It offers a lot of cool features like the ability to perform spell correction or fuzzy matching for users that are typing in difficult queries. It also allows you to create lightweight ranking functions to sort the suggestions in order to meet any specific business objectives that your e-commerce platform might have, right? One last point about retrieving the suggestions. Similar to search, we can have multiple candidate source indexes to retrieve suggestions in like a federated fashion. For example, query names, the queries themselves and the product names can live in like two different indices, and the autocomplete service can retrieve from both and finally blend the results before showing the results to the user, right? Talking about blending, ranking of the suggestions also plays a very critical role in ensuring that the users find relevant query suggestions at the top. A simple way of ranking is sorting all matching suggestions by their popularity. You simply take the frequency of the search queries in the past n months, and you can also enhance this by considering historical trends, like how popular was this query around the same time last year and so on. A slightly more sophisticated method would be what we call the autocomplete engagement model. I'll talk about this a bit more, but this autocomplete engagement model considers more features like the likelihood of users engaging with a suggestion for a given prefix and so on, right? For the rest of the talk, I will dive into a case study about how Instacart implemented an ML-driven autocomplete. All of the content is taken from an excellent blog post by Esther from our team. I'd highly recommend everyone to check out in case you want more details, right? Before diving into the actual post, I'd like to talk about the scale of our data. A key part of Instacart's vision is to be a strong partner to all the retailers that consumers know and love across US and Canada. We serve 800 national, regional, and local retail brands in 70,000 stores across 5,500 cities in US. Overall, we are talking about more than 1 billion products that our search operates over. Now, I agree that a billion is not exactly mammoth scale. However, the diversity in the categories of these products is what makes the problems very challenging. Our retailers carry products from multiple categories, including traditional grocery, pet products, alcohol, electronics, beauty, and so on. Coming to our queries themselves, we were at like a manageable size for a grocery vertical search engine before 2020. However, as our user base started growing, so did the range of queries that our newer users issued. Users enter like a wide variety of searches, including broad searches like lunch, medium intent queries like low calorie drinks, very specific intent queries like frozen yeast rolls, and also like non-grocery queries like Xbox gift cards and so on, right? So let's now talk about what kind of challenges does this pose for Instacart when we started building our autocomplete functionality. The first issue we had to tackle was generating a comprehensive set of query suggestions that is also tailored for individual retailers. By analyzing past customer searches on Instacart, we were able to generate a comprehensive set of suggestions that would be used for predicting the user search queries. Utilizing a data set that is directly derived from our search logs has the advantage of offering natural language suggestions, which are very relatable to the users. In addition to generating the suggestions themselves, we employed like a set of filters to ensure that the user query is like well formed. These filters included eliminating any suggestions that contain offensive terms or any blocked words and so on. Discarding any suggestions that use words outside of Instacart's defined vocabulary specific to shopping intent on our platform. Removing any suggestions that were too lengthy, removing duplicate forms of the same words, for example, eggs and egg, and we kept only like the most popular version. Right. So all of this, it does create like a corpus of very solid query suggestions and so on, so that we could be showing to the user. Once we had this data set, the next challenge we tackled was to remove any redundancy in the suggestions that a user sees. Offering semantically identical suggestions can overwhelm the user with unnecessary options and make it look like the user's intent query will be surfaced, right? So for example, like organic bananas and bananas organic, right? I mean, like, so these are semantically similar queries. Probably there are better examples I could give out, but the point is further eliminating these duplicates and so on as such will result in a more varied set of results. So to achieve this semantic deduplication, we used pre-trained query embeddings to identify pairs of terms that are semantically similar. The query embeddings were originally trained on like a search relevance task to identify the best matching products for a user's query. And we were able to reuse them for the query similarity task as well. Right. So once we were able to like further fine-tune the query suggestions that we wanted to show to the user. We set about solving a typical cold start problem that we see for Instacart. Since we rely on historical search logs to generate the suggestion candidates, we would not have any suggestions for a new retailer that onboarded to our platform, right? So relying on like a common suggestion data set for all the retailers might produce irrelevant suggestions. So for example, you could end up showing like bananas at like a beauty store like Sephora. So we had to create tailor-made suggestion data sets for each individual retailers. We solved this problem using our product catalog data to enhance our understanding of search terms, products, and generate query suggestions to assist new and smaller retailers with lower search traffic. This is achieved by utilizing products that are commonly shared across all of these retailers and mapping them to the queries that these products generally tend to convert on. And thus, we were able to solve like the cold start problem for the retailers, for the low traffic retailers, right? Now, finally, let's talk about how we used autocomplete to balance user versus retailer versus platform goals. So autocomplete is a great lever to guide customers to better search experience and improve overall search performance. We discovered that we could further drive business value by jointly optimizing for autocomplete engagement, which optimizes for helping users find what they want, looking for them faster, and so on, as well as add to carts, right? I mean, like, so autocomplete engagement rate is optimized for helping users find what they want, while add to carts as an objective is geared towards driving the search traffic towards higher converting queries. Right. Furthermore, retailers and CPG brands want Instacart to be like a gateway to discovering new products, especially in like non-grocery verticals and so on. So we have different players wanting different objectives. So we started approaching all of this as like a multi-objective optimization problem, where we built individual models for these objectives, and then some more models on top of it that try to balance these objectives. Right. So the balancing models themselves try to ensure that there is like a good diversity in terms of like candidate suggestions and so on that satisfy these objectives, right? Let's now talk about like ranking about, and hopefully that will give a more clearer picture about the point that I'm trying to make. So our very first autocomplete ranking model was based on popularity, which worked fairly well. However, as autocomplete usage increased, we asked ourselves like a lot of important questions. Can this be used to influence a user search behavior? Can it be used to drive even more incremental basket sizes? Also, can we inspire users to search for novel queries or products that they haven't like tried before and so on, right? So all of this led us to exploring new ranking models to determine the final ordering of the suggestions. Since low latency was one of our primary focus, we initially developed a lightweight ranking algorithm. We modeled this as a binary classification problem and incorporated query features such as popularity, as well as features around prefix and query interaction. For example, given a prefix, how many times did the user interact with a particular suggestion and so on as such, right? Or what is the probability of interacting with a given query suggestion? So this approach, this new ranking model led to an improvement in the autocomplete engagement rate and a reduction in the average prefix length, which is the metric about how many characters do the user type typically before they select like an autocomplete suggestion. And all of this allowed the customers to reach search results much more quickly by typing lesser. Right. So in the autocomplete engagement model that I described earlier, we trained the ranking model to optimize for autocomplete conversions or autocomplete engagement rate. However, if you look at it from an Instacart's perspective, the ultimate goal for search is to assist customers in building their cart, right? To align our model with this goal, we created a new training data set and developed a multi-objective model with the primary aim of increasing add to cart conversions, right? To this end, we created an add to cart model that estimates the conditional probability of an add to cart given a term and combined this with the autocomplete engagement model through a model aggregation approach, right? I know this is a lot of details, but you can go check out the blog post or ask me questions here, and I'm happy to answer any questions in more detail. Now I'll talk a bit about the business impact that these various models had when, right? I mean, so the autocomplete engagement model that I described this at the start, for example, increased engagement rate as well as search conversions. Engagement plus the cart ads model, the multi-objective model that I described in the last slide, in addition to the engagement rate, we also drove basket size and also revenue as well, right? So which was great. So we were like, hey, look, autocomplete can be used to increase revenue as well for the platform. So why don't we try optimizing for revenue as well? So we experimented with a model that optimized for all of these three objectives jointly. Interestingly, what happened though was revenue did go up, but engagement rate went down, which showed us that, hey, probably like the current model that we have isn't optimizing for all of these objectives together, or at least these objectives are definitely not correlated with each other directly. So right now, what our team is doing is using further signals to optimize this in a personalized fashion as such, so that we're able to lift all the boats or increase all the objectives, metrics for all of the objectives instead of one hurting the other. Right. We are doing this personalized model by considering long-term user preferences, as well as signals that are in session that are derived from the current user session and so on, right? We're almost at the end of the talk. I'd like to summarize like the key takeaway of our journey so far. And that would be that autocomplete can be used to gain insights into the user's needs and guide search behavior. And we can do this in a way that balances the goals of the user, the retailer, and the platform as well, right? We're almost at time, but I would like to make one last point that running sophisticated machine learning models, like the ones that I described above, the ones that I described previously, requires like a dedicated low latency service that fetches features in parallel and houses models that can output predictions as quickly as possible. So for this purpose as such, apart from having that fast in-memory data store that can do some simple lightweight ranking, we also created a dedicated service that can help us do or run much more sophisticated ML models, right? Yeah, that's all I have. I know this talk probably like packed a lot of things and so on and such, so I'd like to leave time for Q&A. So.
We have some questions in the Q&A. We have one that says, can you suggest any reading materials for semantic deduplication?
Cool. Yeah, this is a great question. So basically, like you can check out Esther's blog post that I linked to, and it contains a reference to another blog post about the search relevance model. We also have like a SIGIR workshop paper on this that you can check out for more details about how we train the model, the specifics about the training objective, how we collected the data set, and so on. So a short answer is please read the blog post by Esther. I can link it here.
And we have another question that says, are searches tailor-made for every grocer, Safeway, Kroger, etc., or for every individual store? Do search patterns among the same company differ across stores across the US? How to account for that?
Yeah, so the searches are tailor-made for every grocer, not individual stores. We do have some variances across zones and so on. So people in New York might see different suggestions from people in California. It's definitely not for individual stores and so on, right? Do search patterns among the same company differ across stores across the US? They definitely do. The same grocer might carry very different inventory based on the city they're in or the state they're in and so on. So the search patterns definitely differ. How to account for that? This is a great question. So what we started doing was, for at least for autocomplete and so on and such, we started generating data sets that are very specific to the zone, and the ranking contains functions that are specific to a zone. A zone refers typically to, let's say, a state, right? I mean, without complicating things further and so on and such. So we both use these specific, we use this geographical information to generate specific data sets for that region, as well as to influence our ranking as well. Cool.
Someone asked, can you please share where you are hosting the ML models and how are you embedding the ML models with the search queries?
Yeah, this is a great question. I mean, so we have an internal ML platform or ML serving platform, which we call as Griffin. This was again shared by the details of this were shared by like an excellent blog post by the ML infrastructure team for Instacart. I would recommend you to check that out. This ML flow ML CLI, which is like the internal tool for on which Griffin encapsulates as such. It helps us it helped us with a lot of things. So for example, it first created like a very fast feature store that allows us to fetch features very, very fast. Right. And it also helped us provision systems that can help us run all of these models in like a low latency setting. Again, like the answer is too broad. I would ask you to like probably check out Instacart's blog post on this. And
yeah,
right, sorry.
No, you can go.
Yeah, I mean, so people are asking, how can I find all of these links and so on? So like probably I can just type in the chat or share somewhere.
Sure. Or if you share it with me, I can make sure that the people who attend get access to those.
Cool. Sounds good.
Is it the same like Instagram suggesting the pages based on our location?
Is it same like Instagram suggesting pages based on our location? So we do use some location features and so on as such. Unlike Instagram, I don't think we are optimizing for engagement and so on. So okay, I mean, like basically we do use like a lot of location-based features and so on as such. This is to make sure that we tailor or we capture like the regional preferences or geographical preferences that, for example, users in the same zip code might be sharing very similar taste preferences and so on as such, right? So we do have some of those features. We also realize that that might introduce bias into our models as well. So we are very careful when using features like this as well. I hope that answers the question. In short, we do rely on geographical specific features, but those are just one of the features, some of the features that are used. It doesn't tell the full story.
All right, I think we have time for one more question, unless it doesn't take so long to answer, so then we have two. Someone asked, how do you calculate engagement rate? How do you calculate search conversions? Conversion to what? Okay,
yeah, so sorry, I should have clarified that better. So engagement rate essentially refers to the number of times people, for all of the searches that are done on Instacart, what percentage of those come from engagement or a user tapping on an autocomplete suggestion, right? So the number of times people tap on an autocomplete suggestion divided by the number of searches that are done across a period of time, right? How do you calculate search conversions? Again, I should have been more clear about this. Search conversion typically refers to user adding an item to the cart based on the search results that are shown.
And then one more, and this will be the last question. Can you talk in detail about multi-objective learning, in particular, the model that combines individual objective models?
Yes. So basically, like again, I cannot talk in details in this particular talk. I think it's a big topic for sure. First, I would like you to check out that blog post, which has a lot more details about a few different approaches that we tried. I'll leave you with like the last one as such, right? I mean, like, so multi-objective typically refers to like For us, at least, it refers to achieving a balance between different objectives that we might have. So in this case, autocomplete engagement rate is one objective. Adding to cart is one objective. Revenue could be like another objective, right? So for each individual user, how important this objective is, or how important each objective is, or to the platform, how important each objective is dependent, very much dependent on the context. There is no one right answer. Therefore, we train models. So for example, contextual bandit models as such really help in personalizing deciding in a personalized manner on which objective is right, how much weight we need to give on each objective based on where the user is at in their shopping journey, what retailer are they typing in, what are the items in the user's cart, and so on as such, right? So right now we are trying out models like that, or we will be trying out models like that, which will give us like a much more personalized and a contextualized answer. There are many different ways to go about like doing multi-objective optimization. Again, like the blog post has details about some of the approaches that we tried and why we chose this particular approach about label aggregation that I discussed in the earlier slide.
Awesome. Well, thank you so much. I know people still have questions. We can find time for maybe another chat in the future. If you're interested in watching the recording, we'll have that up for you later today. Thank you so much for joining us, and bye, everyone.
Thank you.